Hello, everybody. Thank you for being here. Thank you for the organizers for allowing me to give a presentation on Fibonacci numbers. So we're familiar with Fibonacci numbers, right? The Fibonacci sequence is a sequence fn defined recursively by taking the first two numbers to be equal to 1, and then any number is obtained by adding the previous two. And a few of the terms of the sequence are the numbers 1, 1, 2, 3, 5, etc. What I'd like to do is to find identities for powers of the Fibonacci sequence when the position of the terms in the sequence are equally spaced. So, for example, right, the identity that defines the Fibonacci sequence f sub n plus f sub n plus 1 minus f sub n plus 2 equals to 0 is an example of such identity where the power of the Fibonacci terms are equal to 1 and the terms are equally spaced at distance 1. What I would like to do is to also change this to power 2. So put power 2 over here and see how do I do that. Or change the n and here put n plus 2 and then it would be n plus 4, right, by distance 2 or distance 3, right? Whatever I have to do in order to get such identity. So in the case that you look at equally spaced by distance 1 consecutive terms of the Fibonacci sequence, that problem was solved by Jardin. So, for example, when the power is 2, this identity found by Jardin is fn squared minus 2 fn plus 1 squared minus 2 fn plus 2 squared plus fn plus 3 squared is equal to 0. And he did this for any power. Power 3, this is identity for power 3, power 4, etc. Okay, so these are all well-known identities, right, for consecutive terms of the Fibonacci sequence by changing the power 2 to 3 to 4, etc. So this switch in the consecutive is what I'm going to call the shift. Okay? So what I'm going to describe the shift operator, and what I'm going to do is I'm going to assume that V represents the infinite dimensional vector space of all sequences of complex numbers. An element of V is a sequence X whose nth value is denoted by X sub n. So the shift operator, right, takes a sequence X, and S of X is a sequence whose nth value is X n plus 1. So if you apply it one more time, you shift by 2, right? And so it's no surprise that if F is the Fibonacci sequence, the identity plus the shift minus the shift square applied to the Fibonacci sequence is equal to 0. So Jardin's identities can be written in operator form in this form: identity minus 2 shift minus 2 shift square plus shift cube of f squared is equal to 0. And the other operations are, go in this form, right? So this is for f cube and this is for f to the 4. So we have a way to obtain this. But what I would like to do now is to take other separations. This is separation 1, right? So I would like to take separation 2, right? And so and to keep the f squared, for example, right? So that's where I'm going with this. So what I'm going to do is I'm going to think of each of the identities as polynomial in S. So what I'm going to do is I'm going to take a polynomial with complex coefficients a sub k x to the k, right? And I'm going to substitute the power x to the k by the kth iteration of S. So the polynomial applied to S will be the same coefficients, but with a iteration k of the shift operator. 0 iterations of the shift operator gives you the identity. So I'm rephrasing the problem by trying to find, given a power k and a common distance between the terms d, we want to find a non-zero polynomial pkd such that pkd applied to the shift operator gives an operator that when I apply it to the kth power of f, it gives me 0. And so in my paper, I prove that you can take the this polynomial to be exactly the polynomial that appears right here. Okay, so this polynomial essentially has an alternating sign over here, right? This is not quite alternating, but think of this as alternating. And then over here you have what are called the Fibonacci numbers, the D Fibonacci numbers. The D Fibonacci numbers, right, are defined just like you define the binomial coefficients, but in this case you use the Fibonacci numbers f sub kd, f sub k minus 1d, etc., right? And over here is the factorial part, right? Um, this definition does not make sense when the j is 0, but you define it to be equal to 1 when the j is 0 so that the theory will work. Okay, so that's part of what I had to do to make it work. And so these numbers, all you have to do is just compute them in this form and you are good to go. So here you see the polynomials that I construct. Here is the one that gives you the Golden ratio, right? 1 plus x minus x squared. But you can see many more over here. And when you transform this into the identities for the Fibonacci numbers, you are going to see these identities, right? So the first row is the one that defines the Fibonacci sequence. And then you can see over here, these are the identities that Jordan found, right? But you can see also distance 2. Let's look at this one. Fn minus 3, Fn plus 2 plus Fn plus 4 is 0. And if you put squares, Fn squared minus 8, Fn plus 2 squared plus 8, Fn plus 4 squared minus Fn plus 6 squared is equal to 0. And so all of these identities now come from the construction of the polynomials for which we already found formulas. So this leads you to this table of identities over here. Okay. Now, a surprising fact is that one can replace the Fibonacci sequence by any generalized Fibonacci sequence, and the qualities in the previous slide will still hold. That is, if Gn satisfies that Gn plus Gn plus 1 is Gn plus 2, then all the qualities in the previous slide still hold when the Fn is replaced by Gn, right? So you substitute in all the qualities, in all these qualities, you put any generalized sequence, like the Lucas sequence, if you're familiar with the Lucas sequence, that will hold over there too. And that's the motivation for the construction, actually, of the polynomials pkd that I actually constructed earlier. So this is a very surprising fact, right? It's unexpected at this moment, right? But it's expected if you once you read the paper, you understand that I did this construction for any generalized sequence. So the polynomials PKD have some interesting properties. So an example, right? So if D1 divides D2 as an integer, then PKD1 divides PKD2 as a polynomial. That's surprising. PKD always divides PK plus 2D when D is even. Or PKD always divides PK plus 4D for any D, right? So even when D is odd. Now, these polynomials don't divide each other when the K1 divides a K2, but you can renormalize. So if you renormalize PKD by putting power x to the k instead of x, then you get a new polynomial. And these polynomials actually do satisfy the property of divisibility. That means this polynomial Q1 D1 divides Q K2 D2 if either K1 divides K2 or D1 divides D2. And P1KD divides QKD always. Okay. Now, these properties of divisibility, right, are seen in this table. This is a table for QKD, right? Q11, is the same as P11, 1 plus x minus x squared. And this divides every single polynomial that you see over here, right? Q21 divides Q41 or divides Q42 because 2 divides 4, right? Q22 is divisible by Q14 because 2 times 2 is 4. So Q14 divides Q22, etc. There's lots of divisibility properties in this table that appears right here. They're very interesting properties. And these leads you to properties of coefficients, right? So when you have these, the properties, for example, this property over here allows you to relate coefficients k plus 1 in the row k plus 1 to coefficients k plus 2, like the binomial coefficients, right? This is kind of like the binomial coefficients, but this is for binomial coefficients. And the index k, right, can be switched to index k plus 2 by this identity over here, right? So these all of these are identities that come from the divisibility properties of the polynomials. Another one that comes over here, but this one changes the, look at the index over here. This is a 2D over here, and these over here are D Fibonaccials. So you can relate D Fibonaccials to 2D Fibonaccials. Again, something which is not necessarily expected. Another consequence, is that if you take any generalized sequence, G sub n, then this gives you a linear dependence between k plus one of them, right? And so, this is very similar to this other one. This is the one that my paper proves, right? Which is the one that I announced earlier for the construction of the polynomials PKD. Well, this is identity that it gives you, and you can see that also it gives you something different, right? Where you switch the power k over here from the power and you put it in the index below, right? And that game is it's an interesting game to play, right? So this k over here goes over there too. And all these results also generalize um, to other more general Fibonacci functions, right? Where the Fibonacci functions are obey this kind of law. And the Fibonacci polynomials start with f1 of x equals to 1 and f2 of x equals to x. So in order to prove all these identities, I construct the polynomials PKD in such a way that they annihilate any Fibonacci generalized Fibonacci sequence. And in order to construct it for general sequences, I do a symmetrization operation that involves units, primitive units or primitive roots of the unity. Okay, so the details are in my paper, right? You can find my paper here in this website, and you can find it using the Google search engine by searching for the title of this presentation, and you will get to my paper. Thank you very much.